Hello everyone. So today's topic, technical topic for YouTube live presentation in Semicon is synthesis in VLSI. So Semicon Technolabs, as we know, it's like 8+ years of experience in teaching the students, right? Over 8+ years of experience, headquartered in Bangalore and a branch in Hyderabad. So, Semicon provides a high quality industry relevant training in physical design, analog layout, analog circuit design, DV, DFT. So, a few words about the presenter. So, Casey has 19+ years of experience in VLSI and currently working as Senior Director at Radiant Semiconductors, taking care of end to end product development. So, let's talk about the ASIC design flow, right, and understand where synthesis exactly comes into picture. Okay, so as we can see in the ASIC design flow, so first is system specification, where we come up with an idea and then try to understand what kind of chip we are planning to do, whether it is medical application based, automobile industry based, or IoT based, consumer application based. So what type of industry we are catering to, right? And once the idea is finalized, this has to be mapped into architectural design, which is nothing but architectural document that is written out by the architects, right? Again, in the architectural document, we have analog portion and digital portion. Let's talk about the digital portion because today's topic is synthesis, right? So the digital portion of the architectural document is mapped into RTL design by the RTL designers, and then functional verification of the RTL has to be done before it can be moved on to the synthesis stage. Only when the functional simulations are passing, then the RTL is provided to synthesis. The synthesis team will convert the RTL or map the RTL into netlist, right? Now, this gate level netlist, which is technology dependent, this is moved on to physical design step, which is nothing but backend, right? Anything below physical design and below, these steps are called as backend, and anything above physical design, right, all the way till DFT, that is called as front end. Now, in physical design, we do place and route in order to map the gate level netlist into layout, right? And this is followed by sign-off checks. And once sign-off checks are clear on the physical design database, then we go for mask preparation, fabrication, packaging, and testing, and finally finished chip. Okay, this is the entire ASIC design flow. Now, today's topic is specifically focused on synthesis. Okay, now what exactly is synthesis? Synthesis is the process of converting a high-level hardware description language, HDL language, design into gate-level netlist. Okay. Now, this HDL language can be either Verilog or VHDL. Okay. So usually for regular applications, we go with Verilog because it is easy to test as well in the functional simulations, right? But then if the code needs to be secured, right? I mean, let's say for military applications, okay, in those cases we go for VHDL. All right. Now, most of the code we go with Verilog because in general for consumer applications, automobile and all, Verilog code is the best preferred one because of functional verification, ease of functional verification. Okay. Now, either in Verilog or VHDL, once we write the code, initially we write the code in behavioral modeling, then we map it into structural code, and this structural code is then mapped into gate level netlist, technology dependent gate level netlist. So, synthesis is the process of converting a high level hardware description language into gate level netlist. Okay, there are various steps that go into synthesis. Once the RTL goes through all those steps, finally it is mapped into gate level netlist. Okay, the goal of synthesis is to generate a gate level netlist that meets the design specifications and constraints such as area, power, and timing requirements. Now, it's not just about mapping the RTL into gate level netlist, right? We also need to make sure that the gate level netlist is optimized well in terms of area, power, and timing. Okay, this is what we do in the compile stage. right? So in the compile stage, our entire focus is to optimize the PPA as much as possible based on the design specifications and constraints that has been given to the synthesis domain. Okay. Now, what are the inputs for synthesis? Right, again, synthesis can be classified as logic aware synthesis and physical aware synthesis, but then we have listed out all the inputs which needs to be given, whether it is logic aware or whether it is physical aware. Let me outline these inputs one by one. Okay, the first one is RTL code. Okay, as we discussed, the structural RTL code either written out in Verilog HDL language or written out in VHDL HDL language. This is the first input what we need to give. Okay, register transfer level. RTL stands for register transfer level, right? Now, second input is logical library .lib. Okay, so logical library is nothing but the timing library. So this is given by the foundry. So this library contains cell area, cell leakage power consumption, cell internal power consumption, cell setup time, cell hold time, and a lookup table. Right, I mean, this lookup table is used in order to arrive at the cell delay. Right, and even the logical library contains the wire load models, which are used for net delay calculation in the absence of physical TLU plus files or physical extraction files, or the physical .tf file or physical tech.left file. Okay, so we can use logical library for timing point of view, logical point of view, okay, and even for extraction point of view using the wire load models. Okay, so this is given by the foundry. .lib file is given by the foundry. Okay, now physical library .left. Okay, so physical library is applicable only when we are doing physical aware synthesis. Okay, if we are doing only logic aware synthesis, then we don't need to give physical library .left file. Okay, the physical library contains physical aspect of the cells. It can be metal layers information, right? It can be area of the cells, right? It can be cell site. So physical information of the cells is present in the physical library, right? And it can be related to standard cells or it can be related to macros as well. Macros and standard cells, to briefly touch base both of them, standard cells are smaller in size, macros are bigger in size. Okay, and again, in standard cells we have two types. One is combinational and another one is sequential, right? Now, combinational cells are not controlled by the clock signal. They perform the functional operation as defined in the logical libraries. Okay, whereas sequential cells are controlled by the clock signal. They store the data. Okay, so generally that's why in the timing perspective we have reg to reg, where like we have combinational logic in between two registers, and the operation or the data transfer between the registers is controlled by the clock signal. Okay, now this physical library is again given by the foundry, and this is applicable only when we are doing physical aware synthesis. Alright, now technology file. Technology file again is given by the foundry. So technology file .tf is for Synopsys tools. If we are using Cadence tools, then it is .tech.left file. Okay, now technology file contains metal layers, routing direction information, metal layer spacing information, vias information, right, and then metal layer pitch information, all the information that is needed by the router in order to come up with a proper grid, routing grid. That information is present in the technology file. Okay, we can also have the metal stack information present in the technology file. Okay, now this technology file is applicable only when we are doing physical aware synthesis, and this technology file is given by the foundry. Alright, now wire load models file. Okay, we can have either wire load models file which is a separate file, or we can have the wire load model file which is combined inside the logical library file. Okay, because logical library file also contains wire load information. Okay, so this wire load model again, it is of three types: top, enclosed, and segmented. Okay, we can choose whichever appropriate for our project. Alright, so wire load models are nothing but they contain the R and C values which we use for net delay calculation in the absence of the regular extraction files or the regular technology files. Okay, generally wire load models are used in logic aware synthesis. Okay, in order to come up with the net delays. Now Synopsys design constraints file. Okay, so we have initial timing constraints given by the RTL team, generally that is in the tickle format. So RTL team provides us clock definitions, how many master clocks are there, what is the clock frequency or the clock period that is associated with each of these master clocks, what are timing exceptions that needs to be applied, right? So this is the first cut information which we receive from the RTL team. Okay, now, using this information and using the design specification and the design constraints, right? I mean, we try to come up with the clock uncertainty, derates that needs to be applied, input delay and output delay that needs to be applied at the interface, set driving cell, set drive at the inputs and set load at the outputs, right? Set max transition. So all the remaining constraints, including some of the generated clocks, right? We try to come up with the rest of the timing constraints with the help of the timing constraints team. Okay, so timing constraints team will help us to come up with the remaining set of constraints that are not provided by the RTL team initially. Similarly, design margining team will help us to provide how much of uncertainty we need to keep, max transition we need to keep apart from the one that is already present in the library, because max transition is already present in the logical library. Similarly, max capacitance. But however, in the timing constraints file, we give pessimistic max transition values so that it will reduce the cell delays and more number of levels of logic can be placed in the given clock period, right? Similarly, we can increase the clock frequency as well by reducing the clock period, right? These are some applications of going with pessimistic transitions. Okay, and similarly electromigration violations also will come down if you go with pessimistic transition values. But however, please bear in mind that the drawback of increasing the transition values pessimistically is it will lead to increase in area as more and more buffer cells need to be added in order to meet the pessimistic transition values. Okay, then unified power format, UPF or CPF. Okay, so this UPF or CPF, it can be applicable for both logic aware and physical aware. This also comes from the RTL team, just like how the timing constraints, initial timing constraints come from the RTL team. In the same way, UPF also comes from the RTL team. Okay, now RTL team will provide the UPF if the design is targeted for saving the power. Okay, in the PPA requirement, if power is the main criteria that needs to be kept in mind and performance and area is secondary, right? In that case, to save the power, we need to break the entire design into multiple portions, and each portion can be independently turned on and turned off. And this can be done by keeping each of these portions into power domains, which we physically call as voltage areas, right? And these individual voltage areas can be controlled to turn on and turn off, thereby saving the leakage power and dynamic power, right? And dynamic power, as we know, internally again it is of two types. One is internal power and another one is switching power, right? So in general, once we divide the entire logic into multiple portions and keep each portion into different power domains and voltage areas, and individually if we can turn off these power domains and voltage areas, automatically the power consumption will come down, because logic is not switching, logic is completely turned off, even the leakage power consumption is zero. Okay, that's the intention behind going with either UPF or CPF, right? Apart from our regular other techniques like clock gating, self gating, dynamic voltage frequency scaling, so many other power saving techniques are there. But the advantage of going with the power format file, it can be UPF or CPF, is to create the power domains and to turn off the power domains when not in use. Okay, that's the advantage. Okay, now these are some combined inputs for either logic aware synthesis and physical aware synthesis. Okay, now quickly to recap, RTL code is needed for both logic aware and physical aware. Logical library, this is again needed for both logic aware and physical aware synthesis. This is coming from Foundry. Physical library, this is again coming from Foundry and it is needed only for physical aware synthesis. Technology file, this is again coming from Foundry and it is needed only for physical aware synthesis. Wire load model file, this is again coming from Foundry. Either it can be coming as a separate file or it will be sometimes combined in the logical library. Okay, so this wire load model file is used only for logic aware synthesis. Then design constraints, this is coming from the RTL team in the tickle format. Then UPF is again coming from the RTL team. Okay, even CPF is coming from the RTL team. Okay, CPF is common power format. This is the power format for Cadence tools. UPF is the power format, unified power format. This is the power format for Synopsys tools. Okay, now let's go a little deeper into individual inputs. Right, in this particular technical session, let's go through what all things are present in the individual inputs. Okay, RTL code, as I mentioned initially, we come up with the behavioral HDL RTL code. It can be either Verilog or VHDL. This behavioral RTL code is mapped into structural RTL code. This structural RTL code, after functional simulations are clean, then they will be given to the synthesis team for mapping into technology dependent gate level netlist. Okay, now RTL code HDL, here there is a sample of the Verilog RTL code. You can see the module adder 4-bit. Okay, and there are inputs, right, and there are outputs, and there is functionality that is defined. Right, now how this is mapped into gate level netlist. Okay, the module name exactly remains same, adder 4-bit, right, and then you have inputs and outputs as defined in the left side RTL code. However, the functionality assign sum equal to a plus b, right, I mean this has been mapped into the corresponding logic gates. Here you can see XOR and AND. Okay, XOR and AND, XOR and AND, XOR and AND, first bit, second bit, third bit, fourth bit. Okay, so using the XOR and AND gate, we were able to map this adder 4-bit module that is present in the RTL code into technology dependent gate level netlist. Now this XOR is technology dependent logical cell, AND gate is technology dependent logical cell. Okay, now this is how the RTL code is getting mapped finally into technology dependent gate level netlist at the end of the synthesis. Okay, again this mapping of gate level netlist needs to be optimized with respect to power, performance and area, right, which is taken care in the compile step of the synthesis. Okay, now let's go little deeper into another module, sample module in RTL. Okay, let's take module and 3x4 RVT. Okay, again we have output, input, and this is the functionality what we are looking at, and this is the spec param what we are looking at. Okay, now these are the different modules or different RTL codes what we have, right, which will be finally mapped into the gate level netlist. Now let's look at the logical library. Okay, Liberty timing library, it will be in .lib format, which will be mapped into .db format if we are using design compiler, which is the most used sign-off tool in synthesis. Okay, so design compiler or design compiler topographical, design compiler graphical, all these tools they use .db file. Okay, the reason being it is a smaller version of .lib file, the file size will be smaller and it will be easy to read these files in very less amount of time. Okay, now this Liberty timing file, right, either in .lib format or .db format, which we are going to generate using .lib format. Okay, so it contains cell logical view or timing library, standard cell lib, macro lib, IO lib, gate delay function of input transition time and output capacitance. As I mentioned before, like we will be having the lookup table. In the lookup table, based on the input transition and output load, we will be coming up with the gate delay. Okay, so lib contains a cell type and functionality. Okay, functionality will be clearly defined in the lib. Okay, cell type, right, what is the name of the cell, how many types of drive strength are available, right, everything will be captured in the lib. Then delay models, either it can be wire load model or NLDM or CCS. Okay, generally we go with CCS model. Okay, because CCS is the most advanced and we will have even CCS, signal integrity based libraries as well. Okay, pin and cell timing and design rules. Okay, then PVT conditions, it can be slow, fast, typical, right, and so many other library corners are also available in order to take care of the variations. Okay, global variations. Then power details, right, leakage and internal short circuit power. Okay, so we will be having the internal short circuit power. Okay, so if you can see on the right side, combinational cell info in .lib. Okay, this is a buff D0. D0 is nothing but the drive strength. Buff is nothing but the cell name. We have the area, right, and for every pin we have capacitance, fan out, and there is functionality associated. We have the direction as well, whether it is output, input, in out, right, and internally we have how the timing information is with respect to related pin. Okay, so with pin Z with respect to related pin I, how the timing varies. Okay, this is nothing but arc, timing arcs. Okay, similarly pin I, right, so direction input, capacitance, fan out load, max transition. Okay, I is the input pin, Z is the output pin, right. So this is how a combinational cell info is captured in the .lib file. Okay, now let's see sequential cell info in the .lib file. Okay, cell D flip flop, DFFPOS. Okay, so library cell name. What is the leakage power associated? Area, footprint. Okay, all the cells with this footprint, right? I mean, they are of similar kind of functionality. Okay, input and output ports, the direction input, function A, pin D. Okay, so D is nothing but a direction input. It is the input pin, capacitance, max transition associated. Similarly, clock is again an input pin, capacitance and max transition. Q is again an output pin. And what is the capacitance? Right, timing information, related pin. With respect to related pin, what is the setup rising time, rise constraint? Similarly, fall constraints, since this is a flip-flop. Okay, because in the calculation of data required time, we need to have the setup time and hold time, right, of the capture flop. So that is coming again from the .lib file. Power information, if you look at the power information, we have internal power, right. Similarly, in the very beginning we have leakage power. Okay, so leakage power is present. Similarly, in the dynamic power we have internal power. Okay, switching power is calculated using the formula half CV square F. We can include even the toggle count also. Okay, toggle count half CV square F. C is capacitance, V is supply voltage, F is clock frequency. Okay, now let's look at the lookup tables in the .lib file. This is how the lookup tables will be. LU table template, lookup table template. Okay, index 1, index 2, and this is how we have the values, different values that are associated. Okay, so using this lookup table and calculating the input transition and output load, the tool will come up with cell delay values. Okay, the SDF tool, the engine which calculates the SDF file, the delay calculation engine, right, it will calculate the delays, cell delays from the input transition and output load by using the lookup table. Okay, now .left file, as we discussed in the very beginning, .left file is nothing but physical library. This is needed only for the physical aware synthesis, and this is coming from the foundry. So the left file contains cell name, shape, size, orientation and class. Okay, port or pin name, direction, whether it is input, output, in out, and layout geometries, antenna difference area, obstruction or blockage, because we don't want the routing to happen on top of the cell, right. So macro, right, we have the macro name and then class, block, source, user, origin 00. Any cell origin will be 00 inside the physical library. Then size, okay, what is the size of this cell? Symmetry, right, XY is the standard symmetry and R90 is the standard orientation. Okay, you can modify the orientation based on the side rows that are present in the floor plan. Okay, now let's look at this pin A25. So direction input, when we say direction input for A25 for this particular cell, it has to be the same direction in the library file also, .lib file also, logical view .lib file also. Then this needs to be used as signal. We cannot use A25 as power or ground or clock. Okay, so it has to be used only as signal. Then this is the physical portion of the pin. Okay, so the pin is present in M1 layer and the shape of the pin is defined here. Okay, in this rectangle box. Similarly, we also have the pin in layer C0. Okay, and the shape of the pin is defined here in the layer C0. Okay, using this, the physical design tool or the physical aware synthesis tool will map the physical portion of the pin using this information. Okay, based on the rectangles what are defined here. Okay, Now, standard cell info in the left file. How does the standard cell info is present in the left file? Here is the snippet. Let's take a macro. Okay, XNOR 3 into 2 RBT. The previous one was with respect to macro, SRAM macro, and this is with respect to standard cell. Okay, RBT is nothing but one of the VT flavor. Okay, we have SVT, HVT, LVT, RBT. Okay, so these are the VT flavors what we have. Alright, and then this is class core. Class core means the cells which are sitting in the site rows. That is nothing but the standard cell sites. Okay, so whenever we have class core, it clearly means it is a standard cell. Okay, source user origin 00 size, this is the size of this particular standard cell, 3.8 by 1.672. This is the site height. Okay, site row height 1.672. Okay, the site row height will remain same, width will keep changing based on the drive strength. Okay, 3 into 2 drive strength. Similarly for other drive strengths, the width will keep changing. Okay, symmetry again XYR90. This is common whether it is standard cell or whether it is macro. Okay, site unit. Now if you take the pin A1, okay, direction is input, and we need to use this A1 pin only for signal. Okay, and port layer M1 rectangle. Based on this, the physical design tool or the physical aware synthesis tool will come up with the pin width, okay, for the router to access the connection to the A1 pin. Okay. Now let's look at the tech file. Okay, technology file defines units and design rules for layers and via as per the technology node. Okay, it can be 3 nanometer, 5 nanometer, 7 nanometer, 10 nanometer. Based on that, the units and design rules for layers and vias will change. Okay, name and number conventions of layers and vias. So physical and electrical parameters of layers and vias. Example, direction type, whether it is horizontal or vertical direction, pitch, width, offset, thickness, and resistance. Okay, in our physical design tool or in the physical aware synthesis tool, we can only see the width of the metal layer. We cannot see the thickness of the metal layer. Okay, now measuring grid definition, site unit tile definition. Okay, now this is a snippet of M1. If you see here, M1 is the metal layer 1. Okay, layer number is 11. Okay, mask name is metal, METAL, metal 1. Pitch is 0.152. Pitch is nothing but width plus spacing. Okay, half width plus spacing. Then visible, selectable, these will come in the tool. Okay, color, the color of metal 1 is blue. Okay, and then we have pattern. Minimum width is 0.05. Max width is 5 microns. All these are in microns. Default width 0.05. Min spacing, and then same net min spacing. Okay, so these are the physical rules which we have to follow in order to do the routing using M1. Okay, similarly we can use this for coming up with the resistance and capacitance values as well in the absence of TLU plus files. We can do the extraction also using the tech file. Okay, now tech file info snaps design rule. Okay, layer 1, this is with respect to via, layer 1 via 1, layer 2 via 2. Okay, and then so how should be the cut size? The cut is the one which will connect via 1 to via 2. Okay, similarly design rule, this is for M9. Okay, layer 1, and then layer 2 is via 8. And what is the minimum enclosure we need to have? Similarly density rules. Okay, what is the window size? And then min density is 10, max density is 85. Right, if the density is less than 10 or if the density is more than 85, we need to make sure that either we add the metal density to make it above 10 or we trim down the metal density so that it comes down below 85. This is needed for fabrication. Okay, so this we do it during the chip finishing stage of physical design. Alright, now coming to UPF. What is UPF? We studied about UPF, right? Unified power format if it is synopsis, conformal cadence power format, common power format if it is cadence. Okay, now unified power format or common power format, right, is a critical file used in design for power intent specification during the implementation of complex integrated circuits. Okay, UPF plays a vital role in low power design techniques, enabling designers to manage power domains, power modes, and power related constraints effectively, efficiently. Okay, so as I mentioned before, we have several other techniques to save the power. For example, clock gating to save the switching power in the dynamic power. Okay, similarly self-gating, here also we can save the switching power in the dynamic power. Okay, thereby the total power will be saved. Okay, we have dynamic voltage frequency scaling. Okay, we can scale down the supply voltage, we can scale down the frequency, right, based on the design requirement. There again we are saving the total power. Okay, now why do we need unified power format, or why do we need common power format? Why do we need these files? Is right, if at all you want to divide your entire logic into multiple portions, and each portion can be kept inside a separate voltage area, and these voltage areas can be independently turned on and turned off without disturbing the functionality, right, then in that case you are saving leakage power as well as dynamic power. Tremendous amount of power can be saved, right, because you are turning off the entire design associated with that voltage area. So that's the reason we need to use unified power format and common power format, right? And why do we have the name unified? Right, the reason being this file can be understood by every tool in Synopsys. Similarly, common power format. Common means the CPF file can be understood by every tool in the Cadence world. Okay, Cadence EDA vendor world. Okay, that's the reason we have UPF and CPF. Okay. Now, UPF is one thing which we can give as input to synthesis. This file is initially coming from the RTL team because they are the one who clearly know how to define the power state tables. Power state tables are nothing but which power domain has to be turned on and which power domain has to be turned off. Accordingly, we need to have special cells in the UPF, which is nothing but isolation cells, level shifters, right, enable level shifters, which is nothing but combination of isolation and level shifter cells, retention flops, always on cells, and of course power switches in order to turn on and turn off the UPF. Okay, now let's see what all things that are present in the UPF. As I mentioned, power domains. Okay, sometime design may have more than one power domain like multi VDD design, and sometimes only a single power domain design. So in this way, we can define either multi-supply single voltage or multi-supply multi-voltage. So you can run your design as either using single supply voltage, or you can run your design using multiple supply voltages. Because if you save the supply voltage, if you reduce the supply voltage, automatically your dynamic switching power will come down because of the equation half CV square F. If you reduce your C, that is nothing but load. If you reduce your supply voltage, that is nothing but V. If you reduce your frequency, that is nothing but F. Then automatically you can reduce the switching power of the dynamic power. Thereby the total power can be saved. In this group of elements share a common set of power supply rails, distribution of power in supply nets, ports, supply sets, power state. This is again related to the PDN network, power distribution network, which is used in physical design to supply the current to all the cells. It can be standard cells, it can be macros, it can be IO pads. Okay, additional protection by special cells. So level shifters, isolation cells, power switches, retention registers. Okay, all these special cells are needed if at all you are going with UPF concept, because once you are turning off your power domain, you need to make sure that the last drawn values of the power off state power domain has to be captured in the isolation cells, so that from the isolation cells the next power domain, which is talking to this off power domain, is able to grab the last drawn values of the off power domain. Similarly, if two power domains are having different supply voltages, then to communicate between those two power domains, we need level shifters. Similarly, to turn off the power domains, we need power switches, and then retention registers are needed if at all you want flops to capture the data without turning off even in the off power domain. So all these cells are having secondary PG connections. Okay, now let's go to UPF file snapshot. Okay, how does a UPF file look like? We have supply nets, that is VSS, VDD low and VDD low SW. Okay, these are the two different PG nets what we have, right? And then we are assigning supply set to them, right? And then creating the power domain, and then assigning the supply port and supply net to the power domain, and then we are creating a power switch, right, in order to turn off this power domain. And then in order to capture the last drawn values, we are creating the isolation cells, right? And then finally we are creating the power state tables. Okay, when should be on, when should be off, right? I mean, we are creating the power state tables. Okay, accordingly, based on the content in the UPF, the tools will accordingly map that netlist, map the design accordingly. Okay, now furthermore, So these are the power state tables what we have, right? And then these are the different ports what we have in order to supply the power and ground to the block or to the subsystem or to the chip. Okay. Now TLU plus file. This is again needed only when we are doing physical aware synthesis. So in the physical aware synthesis, we want to do R and C extraction using TLU plus files given by the foundry without using the wire load models that are present in the library. Okay, wire load models are used for net delay extraction only when we are doing logic aware synthesis, right? But then TLU plus files, we use it in the physical aware synthesis when we actually want to extract the R and C of the nets. So TLU plus file is a binary table format that stores RC coefficients. The TLU plus models enable accurate RC extraction results by including the effect of width, space, density and temperature on the resistance coefficients. The map file matches the layer and via names in the Milky Way technology file with the names of ITF, interconnect technology format file. So from the ITF file, we generate the TLU plus files. So sometimes Foundry will provide you ITF file, and from the ITF file, using the utility to map the ITF file into TLU plus file, we need to generate the TLU plus files. But nowadays, of late, in the Foundry PDK, directly we are able to see the TLU plus files. So there is no need to map the ITF file to TLU plus. The main function of this file can be given as finding RC parasitics of metal per unit length. These parasitics are used for calculating net delays. So we generate the SPEF file using the TLU plus files. From the SPEF file, the delay calculation engine will generate the net delays and map it into the SDF file, right, to use for the timing calculation. Now, wire load models, as I mentioned, in the absence of the TLU plus files, when we are doing logic aware synthesis, we depend on the wire load models. Okay. Now, wire load models, the wire load group contains information that DC utilizes to estimate interconnect wiring delays during the pre-layout phase of the design. These models define the capacitance, resistance, and area factors. In addition, the wire load group also specifies slope and fan-out length for the logic under consideration. Okay. Based on the fan out length, okay, the wire load is defined. The capacitance, resistance and area factors represent the wire resistance, capacitance and area respectively per unit length of interconnect wire. Okay, so as you can see here, based on whether the wire load selected is small, medium or large, accordingly we have resistance and capacitance defined. Okay, so these will be used by the extraction engine to come up with the SPEF file, and this SPEF file will be used by the delay engine in order to map the SPEF file into SDF file. Okay. Now, SDC file, timing constraints file. Okay, from the RTL team, we receive the timing constraints file in tickle format. So they generally contain the clock definition, which is nothing but in terms of time period and duty cycle. Similarly, we contain the timing exceptions. It can be false path, multi-cycle path, min and max delay, right? Even case analysis also. Now, constraints for Dolphin, this is one of the project. Okay, so we received the clock period, right? And then what are the ports associated for the clock period, and then which clocks are exclusive clocks, and then input delay and output delay associated with the inputs and outputs. Okay, and we need to remove the clock ports from setting the input delay because clock ports are not associated with the input delay, right? So set load on all the outputs, then case analysis in order to switch between test mode and func mode, right? And then case analysis, right? I mean, where we are exactly setting the case analysis. Okay, now this way we are getting the initial timing constraints file from the RTL team, and then based upon the other parameters which we give during the synthesis with respect to timing constraints, it can be design margins like uncertainty, derates, max transition, total area which we need to achieve, input delay, output delay, set driving cell, set load, set drive, right? So many other factors which we provide, even some of the generated clocks, right, which has to be defined. So all those things will be entering into synthesis loop through the synthesis script, and finally when we dump out the SDC file as output of synthesis, at that time we will have all these constraints defined in the SDC file, functional SDC file. Okay, which will become as input to the physical design. Okay, so with this we will wrap up today's synthesis topic. See you all next week with remaining portion of the synthesis. We will deep dive into how synthesis flow works, what are all the outputs of synthesis, what are the main things we need to look at synthesis, right? And we'll take up any question and answer as well, which are there in the comments box, and then we'll try to cover up in the next week presentation. Okay, so thank you all, thank you for joining us, and please do subscribe to our YouTube channel, and see you all next week. Thank you so much.